Welcome, Calc students, to our third part of the 2.4 video notes, which is still on the chain rule, except in this video we're going to look at some more challenging problems. So just a quick review of what the chain rule actually is. So we know we need to use the chain rule when you have some function of x that's being plugged inside another function. We call it a composition of functions. So when you have something other than plain x being plugged inside a function, you know that's when you're going to have to use the chain rule. So how do we use the chain rule? Well, it basically tells us to just take the derivative of the outer function while leaving the inner function inside untouched, and then multiply the outside of that by the derivative of the inside function. And that's basically what we do. And this right here is just another way of saying what is written here. So this y basically is like the f from here. And we kind of think of it as f of some other function inside. So in this notation, it's referred to as u. So we think of this as f of u, where u is representing that g of x function. It's the same thing as this function that was plugged inside of x. So it wasn't f of x, it was f of some function of x, f of u, so to speak. And then when we first take the derivative of y, notice that we take it with respect to u. That means so dy du you could think of as f prime of u. That means you just take the derivative of f, leaving u intact. So that kind of relates to, or it does exactly relate to, the f prime of g of x right here. And then the du dx is when you then take the derivative of u, that inside function, and now with respect to x. That's now when you finally address the function of x that was inside of f. So this du dx represents g prime of x. So you can call it different things, obviously, and sometimes it's nice to call it u because that helps us think of it as like a single variable, and sometimes it helps us identify the function f more and how we would need to take its derivative and stuff like that. But you can call it different things. The basic gist, though, is that you have one function of x plugged inside another function. You take the derivative of the outer function first, leaving the inside function intact, and then multiplying at the end by the derivative of the inside function. So let's try that here with example 1. So in example 1 here, we're going to look at an equation where we'd have to use a power and a chain rule combination to find the derivative, because I can rewrite this function as -7 times the quantity 2t minus 3 to the power of -2. The exponent is negative since this quantity is in the denominator. I just have to remember to make the exponent negative. But when I write it like that, the advantage is that I don't have to use the quotient rule. I could use the power rule instead, and then the chain rule. So why is the chain rule required here? It's because the thing being raised to a power is something other than plain t. It's a full-on function of t. So we think of that as like our u mentioned earlier, our inside function is 2t minus 3, and so we will need to multiply our overall derivative by the derivative of that inside function, which is 2. So we can think of our outer function, our f of u, as a simple constant n power function. So -7 times this u, this inside function, to the power of -2. So when I take the derivative of the outer part, I'm just doing a simple power rule, multiplying -2 to -7 and subtracting 1 from the power. So what does that look like here? Well, in this context, right, the inside function is 2t minus 3. So when I'm taking the derivative, I basically do a simple power rule, right? 2 times -7 is 14. I keep the inside function as is. I don't do anything with it yet, right? I just leave u right plugged in there. Subtract 1 from the power, so I get -3. And then after I do that power rule, then I multiply by the derivative of the inside function, which is 2. And then, of course, I can multiply 14 and 2 together to get 28. So my derivative is 28 times 2t minus 3 to the power of -3, which is the same thing as 28 divided by 2t minus 3 cubed. And so there's our derivative. We were able to completely avoid the quotient rule by just thinking of this as a simple power function. So why don't you try a similar example over here? Okay, so hopefully this was what you got for your final answer here. 4x divided by 3 times the quantity x squared minus 1 to the power of 1/3. So how do we get to this final answer here? Is by first recognizing that our original function is just a power function with x squared minus 1 plugged inside. So the power here becomes the numerator and the root becomes the denominator of this rational exponent. So all of x squared plus 1 is being raised to the 2/3 power. So I think if I think of that x squared minus 1 as just some sort of inside function, we can call it u. Then I can go ahead and just think of this as u to the power of 2/3 and do a simple power rule. Bring the 2/3 in front, subtract 1 from the power to get negative 1/3. And I just have to remember, since the thing being raised to the power of 2/3 is not just plain x, it's a function of x, I then have to multiply by its derivative. So the derivative of this inside function was 2x. So I multiply that to the side. So 2/3 times this whole expression, x squared minus 1 to the power of negative 1/3, has to all get multiplied by 2x. Then those 2's can multiply. 2 times 2x gives me 4x in the numerator, and then in the denominator would be the 3 and the x squared minus 1 to the power of positive 1/3. So it's negative here, but when we move it to the denominator, it becomes positive. The next thing I want to look at are 2 examples that require some complicated simplifying techniques at the end. Also, we're looking at combinations of product and quotient rule combined with chain rule. So let me first kind of split this up as x cubed times the square root of 1 minus x squared. So I'm going to think of this as u and then this as v from the product rule. So u is x cubed and v is the square root of 1 minus x squared. And then u prime, because I'm going to need to find u prime for the product rule, would be, using the power rule, would be 3x squared. And then v prime is going to get a little bit complicated because I could rewrite v as 1 minus x squared to the 1/2. So taking its derivative is going to require the chain rule because I have this part plugged inside, which is its own function, right? It's something other than x plugged inside. So let's think of that. Since I'm already using u for the product rule, let's think of that as my g of x, so to speak. My inside function, right? So that is 1 minus x squared. So then g prime, the derivative of that inside function, would be negative 2x. And then we'll just think of this as v. So if I want to do v prime, I would need to first think of this as a power rule, where I have this inside part, right, this like blop. Think of that as like a blop on the inside. All that whole blop is being raised to the power of 1/2. So when I'm first taking the derivative of v prime, I begin with the power rule. So I do the 1/2 power gets brought down in front of that whole entire inside function, which is 1 minus x squared. I subtract 1 from the power, so that becomes a negative 1/2 power. But then I have to multiply by the derivative of the inside. I have to multiply this by negative 2x, which is the derivative of this inside blob. So it's the power rule, which is the derivative of blop to the 1/2, times derivative of the blob, derivative of the inside part. Let me simplify that v prime a little bit, because I can see right away like these 2's are going to cancel out, and I have a negative x on the outside times 1 minus x squared on the inside to the power of negative 1/2. Okay, so that's my v prime for the product rule. So that's how I'm going to begin. I'm going to begin using a product rule. So then to find f prime of x, I'm going to do u prime v plus v prime u, because that's what is required. Okay, so I found my u prime earlier. Right here was 3x squared times v, which is 1 minus x squared to the power of 1/2 plus v prime, which is all of that, negative x times 1 minus x squared to the negative 1/2 times u, which was x cubed. So on this second part, I can combine these bases of x. I can multiply them together by adding the powers. So I get 3x squared times 1 minus x squared to the 1/2 minus x to the 4th, I get that from adding the powers, times 1 minus x squared to the negative 1/2. So at this juncture in the problem, we're done in terms of calculating the derivative because we used both the product rule and the chain rule. So we basically finished the derivative part. Now it's just a matter of simplifying this. And what we have here are two different parts separated by a subtraction sign. This part and this part. And the thing that separates them, that helps us see that there's two parts, is the subtraction. In each of the parts, we have this common base of 1 minus x squared. In one part, it's raised to a positive power, and then in the other part, it's raised to a negative power. So what we're going to do is factor out the 1 being raised to the negative power. So I'm going to factor out a 1 minus x squared to the power of negative 1/2 from both of these parts. And so I need to figure out what goes here and here, right? There's a subtraction in between them, but there'll be something left from this part and something left from this part. Now, what does it mean to factor out 1 minus x squared to the negative 1/2? It means that I'm dividing both this and the other piece by 1 minus x squared to the negative 1/2. That's what that means when you're factoring something out. So actually I can see on this right side, what that would do is just cancel out the 1 minus x squared to the negative 1/2 and leave me with x to the 4th. But what I need to figure out is how this part would simplify. I know that there will be a 3x squared because this isn't going to reduce with 1 minus x squared to the negative 1/2 at all, but something will happen with these, and that's what we need to figure out. So let's kind of work off to the side. So if I'm going to take 1 minus x squared to the 1/2 and divide it by 1 minus x squared to the negative 1/2, which again, that's what it means when you factor it out. It means you're dividing it out from both. Well, that means that I'm dividing 1 minus x squared to the 1/2 by 1 over 1 minus x squared to the 1/2, because that's what a negative power means. It means take the reciprocal. But then what does division mean? Division means to multiply by the reciprocal. So I'm going to end up multiplying by 1 minus x squared to the 1/2. And so when you're multiplying these same bases together, you can add the powers. So when you add the 1/2 to the 1/2, you get 1. So this turns into 1 minus x squared to the power of 1, which is just 1 minus x squared. So what do I get when I divide 1 minus x squared to the 1/2 by 1 minus x squared to the negative 1/2? I basically just get 1 minus x squared, which is the advantage of factoring out the one with the negative power. So that's what would be left here. And so now I can distribute the 3x squared on the inside there. So I get 3x squared minus 3x to the 4th minus the other x to the 4th that was in there from this term. And so then I get 1 minus x squared to the negative 1/2 times 3x squared minus 4x to the 4th. And then lastly, I just bring the thing with the negative power down to the denominator. So I get 3x squared minus 4x to the 4th all over 1 minus x squared to the power of 1/2. Or you can think of that as 3x squared minus 4x to the 4th all over the square root of 1 minus x squared. And that, this or this, either or, would be our final answer in simplest form. Now, you saw in the last, or not in the last video, but in one of the prior videos There is also a way to do this by just getting a common denominator. So let me just kind of show you that as another option for simplifying. So let me take it from here again. So let's say I'm here, I have 3x squared times 1 minus x squared to the 1/2 minus x to the 4th times 1 minus x squared to the negative 1/2. Another option is to rewrite them back into radical form. So the 1/2 power would just turn into a square root, and then the negative 1/2 power would be a square root in the denominator. And then get a common denominator between the two fractions. So that first fraction, I would need to multiply by a square root of 1 minus x squared, so that it would have a common denominator with the other fraction. And then right here you can see when you multiply two identical radical expressions together, the square root signs get squared away. They go away. And so then I'd be left with 3x squared times the thing that was inside, 1 minus x squared minus x to the 4th all over the square root of 1 minus x squared. And then you can maybe recognize that's the same as this part right here. And then we can do some simplifying like we had done before. Distribute the 3x squared to the 1 minus x squared. That's all over 1 square root of 1 minus x squared. And then just simplify those like terms in the numerator. 3x squared minus 4x to the 4th all over the square root of 1 minus x squared. And then you can see that you end up with the same answer, but we just kind of simplified it a different way. So you have those two options sometimes. I wanted to show you another one, which we'll do in a second, where the factoring option actually is better than the common denominator option. So sometimes this will be a good option, sometimes it won't, which is why I'm really kind of stressing this factoring process so you can learn how it works. So let's try another one. So this one also, not only is it another complicated simplifying example, but it also shows you a combination of quotient rule and chain rule. So let me start with reviewing quotient rule, because we've got the numerator function, which is u, and then the denominator function, which will be v for quotient rule. So u will be x, and then u prime will be 1. And then v, I'm going to rewrite this as a rational exponent, will be x squared plus 4 to the 1/3. So v prime is going to require the chain rule, because I've got this inside part, this x squared plus 4. So let's think of that as my inside function, my g of x, using the chain rule definition. So that would be just the inside part. So v would just be that inside function raised to the power of 1/3. So I would do a power rule first, keeping the g of x safely inside unaffected, and then I'd multiply by the derivative of that g of x, which is 2x. So I'm going to get, first I'm going to use a power rule, so 1/3 times the whole g of x, the whole blop that's inside there. Subtract 1 from the power gives me negative 2/3. So that was the power rule, which was the outer function here. And then I'm going to multiply by the derivative of the inner function by my g prime, which was 2x. And then nothing really simplifies here, but maybe I'll just bring the 2x in front. So we'll think of this as 2/3 x times x squared plus 4 to the negative 2/3. And then for the derivative of q, I'm going to use the quotient rule. So q prime is going to be u prime v minus v prime u all over v squared. So if I plug all these in for u prime and v and all of that, so u prime was 1 times v, which is x squared plus 4 to the 1/3, minus v prime, which is this whole thing, right? That whole thing is my v prime. So minus 2/3 x times x squared plus 4 to the negative 2/3 times u, which was x. That's my v prime u. All over v squared. So that would be x squared plus 4 to the power of 2/3. Because right now it's to the power of 1/3. But if I square that, I just multiply the powers. So 1/3 times 2 is 2/3. Okay, I'm going to simplify a little here because I have common bases of x, so I can add their powers together. So then I get x squared plus 4 to the 1/3 minus 2/3 x squared, right? If I combine those, times x squared plus 4 to the negative 2/3. All of this is over x squared plus 4 to the 2/3. So I don't know if you're noticing it, but again, I have this situation where I've got these two parts separated by a subtraction. One of them has a positive exponent, one of them has a negative exponent, and also a denominator. So what I'm going to do is factor out the denominator of 3 and the expression to the negative exponent. So from the numerator, I'm going to leave the denominator the same, and in the numerator, I'm going to factor out a 1/3 times x squared plus 4 to the negative 2/3. And the denominator I'm just leaving alone for right now. And so what I have to figure out is what is left from this part when I factor that out, and what is left from this part when I factor that out. And there will be a subtraction sign between them because that's what's separating one part from the other. Okay, so first let's do the x squared plus 4 to the 1/3 divided by these two things. Well, first, let's think of this as having a 1 in front. Let's do the number part first. So if I do, and I'll do some scratch work sort of off to the side here. If I do 1 divided by 1/3, which is what I have got going here, because again, when you're factoring something out, you're basically dividing it from both pieces. So it's like I'm dividing 1/3 times x squared plus 4 to the negative 2/3 from this expression. And I'm again dividing 1/3 times x squared plus 4 to the negative 2/3 from this expression. So when I divide these, I'm dividing 1 divided by 1/3. And when I divide 1 divided by 1/3, I'm basically multiplying by the reciprocal of 1/3, which is 3. So from the 1, I get a 3 when I divide 1/3. Then when I do x squared plus 4 to the 1/3 power divided by x squared plus 4 to the negative 2/3 power, what that essentially is x squared plus 4 to the 1/3 power divided by 1 over x squared plus 4 to the 2/3 power, because a negative exponent means take the reciprocal. But I'm dividing by that reciprocal, so I'm really multiplying by x squared plus 4 to the positive 2/3. That's really what's happening there. And another way to think about that is if you are dividing common bases with different powers, you subtract the powers. You're doing 1/3 minus negative 2/3. And that's another way to understand that it turns into addition. So you can either think of it as subtracting powers or as a negative power being a reciprocal, but then division has you multiply by the reciprocal, so it flips back to the top. This negative power ends up flipping up to the numerator as a positive power, and then I end up adding those powers together. Okay, so then this ends up being x squared plus 4 to the power of 3 over 3, which is 1. So that's just x squared plus 4. So that worked out nicely again. So that's right here. So from the first term, when I factor out 1/3 x squared plus 4 to the negative 2/3, I got the 1 turned into a 3, and the x squared plus 4 to the 1/3 turned into x squared plus 4 to the first. Now from this expression, the x squared plus 4s to the negative 2/3 will cancel out. The x squared will still be there, so I'll just drop that down. And then I just have to figure out what happens if I do 2/3 divided by 1/3. So again, when you're dividing, you multiply by the reciprocal. So basically the 3's just cancel out, and I'm just left with the numerator. So I'm just left with a 2x squared from this second part. Okay, so now, make myself some room here. 1/3 times x squared plus 4 to the negative 2/3 times 3, and I'm going to distribute that 3 to the x squared plus 4. So 3x squared plus 12, and then I have the minus 2x squared from the other term. All of this is over x squared plus 4 to the 2/3. And then that equals 1/3 times x squared plus 4 to the negative 2/3. And then I can combine the 3x squared and the negative 2x squared is just 1x squared plus 12. All over x squared plus 4 to the 2/3. Then what I can do is bring down these things to the denominator. So the 3 is going to go into the denominator, and the x squared plus 4 to the negative 2/3 will be brought down to the denominator as well, and that power will become positive, and then it will add to the 2/3 that's already down there. So then my final answer will be x squared plus 12, because that was all that was left in the numerator, divided by 3, because that came from the 1/3, times x squared plus 4 to the power of 4/3. Since I'm adding another same base with the same power in the denominator, so it ends up being to the 4/3. So then that's my final answer there. And in this setting, since I'm dealing with thirds instead of halves, I feel like it's better to go about it the factoring route to end up at this final answer here. So why don't you guys try something like this with the more complicated simplifying to kind of practice it a little bit. Pause your video, try it with this equation, then come back and check your answer. Okay, so hopefully you ended up with this as your final answer here, the 1 plus 2x squared over square root of 1 plus x squared. This equation, or this derivative, required the product rule again because I had a function x times a function 1 plus x squared. So I called u x and then v the square root of 1 plus x squared. So I had to find each of their derivatives, and for finding the derivative of v, I had to use the chain rule. So I had to multiply by the derivative of 1 plus x squared right here. Then I plugged everything in to the product rule formula and noticed I had the same bases, but one with a positive power and one with a negative power. So I factored out the one with the negative power. This is what I had remaining, and then I combined my like terms, which became my numerator, and then I just moved the negative rational exponent to the denominator and rewrote it as a square root. So example 4 and then the you try after are again looking at equations that use a combination of like a product or quotient rule combined with the chain rule. So in this function here in example 4, I've got this whole thing is like plugged inside. This would be like my u. U is 3x minus 1 over x squared plus 3. And so I could think of this as p of u is just u squared. I can kind of think of it like that. This whole thing just becomes u squared. So first I'm going to do a power rule, but then I'm going to have to multiply by the derivative of u, which is going to require a quotient rule. So let's do that over here. Now, because I'm already using u as my inside function, then let's use f and g for my product rule, okay, or my quotient rule. So let's say that f of x is this top function and then g of x is this bottom function. So I've got these two functions, and then their derivatives would be, so f prime would be 3 and g prime would be 2x using the power rule and the constant rule. Okay, so then for my derivative of u, for my du dx, so to speak, from the chain rule, I'm going to do f prime g minus g prime f all over g squared. So in this case, that will be 3 times x squared plus 3 minus 2x times 3x minus 1 all over x squared plus 3 squared. So then that ends up equaling, if I distribute the 3 and I distribute the negative 2x, I get 3x squared plus 9 minus 6x squared plus 2x, because this negative times that negative makes a positive. All of that is over x squared plus 3 squared. And then that can simplify because I have like terms in the numerator to negative 3x squared plus 2x plus 9 all over x squared plus 3 squared. So this is the derivative of my inside function that I'm going to have to multiply to the derivative of this power rule. So when I take p prime of x, first it's like just doing the power rule. So 2 times all of this, right? 2 times the whole inside blob, 3x minus 1 over x squared minus 3 to the power of 1, right? Because you subtract 1 from the power. That was the derivative of the outer part. That was p prime of u. But now I have to multiply by the derivative of u, which is all of this. I didn't leave myself enough room. Let me write this again. So altogether I get 2 times 3x minus 1 over x squared minus 3 times all of that, negative 3x squared plus 2x plus 9 all over x squared plus 3 squared. And then I think I'll just, so these are like same bases, so I can add the powers when I multiply those. This is like 2 over 1, so I could kind of distribute it to the 3x minus 1. So I'll get 6x minus 2 in parentheses times negative 3x squared plus 2x plus 9 in parentheses. I'll leave that all in my numerator. All over x squared plus 3 to the power of 3, because I add 2 and 1 to multiply those together. Sorry, that should say x squared plus 3 right there. And then I think I'm just going to leave my answer like that. If you want, you can FOIL out the numerator and combine like terms, but it wouldn't serve any purpose in terms of simplifying, so it's also okay to leave it factored. And so we can just stop there. The main point was just recognizing that within this chain rule, I had to use a quotient rule. So why don't you try one where within the product rule, again, we have to use the chain rule. All right, so in this one, we had to use a product rule. So I let secant of theta over 2 be my u, and tangent of theta over 2 be my v. So then to find u prime and v prime, I had to use the chain rule because I had this inside part, which was theta over 2, or 1/2 theta. And remember, theta is like x. It's like our variable, our independent variable. So the derivative of that would just be the constant multiple in front, which is 1/2. So that was the derivative of the inside part for both of these functions. So I had to multiply each of their derivatives by that using the chain rule. So the derivative of secant was secant tangent, and I just left the inside part as is. But then I multiplied by the derivative of that inside part, which was 1/2. And I had to do the same thing with v prime. V is tangent, so then v prime, that would be the derivative of tangent, which is secant squared of the inside part, right? It remains untouched. And then on the outside, you multiply by its derivative, which is 1/2. So then over here, this was u prime v plus, and then this was v prime u. And I had moved the 1/2s in front because it just makes more sense when you're writing trig expressions to have the constants in front. And then I could multiply the tan on the tan to get tan squared, and I multiplied secant squared and secant to get secant cubed. So you can leave your answer like that, or if you want, you can factor out the 1/2. Sorry, it looks like I wrote 1/3. It should be 1/2. You could factor out a 1/2 and a common factor of secant, because both terms have a common factor of secant. And then you could have tan squared plus secant squared on the inside. So you can leave your answer like that as well. So this next example and the u tries that follow are what happens when you have like a triple chain. It's where you have a function inside a function inside a function. So let me rewrite h of theta here to be cosine of 8 theta all squared. So what we have to really be good at doing is like recognizing the outermost layer, which in this case is blop squared, the middle layer, which in this case is cosine of blop, and then the inside, which in this case is 8 theta. We have to really get good at recognizing that because we have to go from the outside in. So the outside function is the whole thing squared. So we're going to use a power rule. The middle function is a cosine function. So we'll be using the cosine rule. And then the inside, the most inside, which is usually our u or our g of x, is 8 theta. So what we're going to do is take the derivative of the power rule first, and we're going to leave cosine inside. So every time you do the derivative of one, you leave the other inside ones alone. So when I go to take the derivative of h, so let's go this way. So h prime of theta first is going to require a power rule. So I'm going to do 2 times the cosine to the power of 1. So everything that's inside stays the same. I do not change it when I'm doing the derivative of an outside layer. I leave the inside layers alone. So I just did a power rule for the outside one. For the middle one, which I now multiply to the end, is the derivative of cosine, which is negative sine. But I leave the 8 theta plugged inside because that was like the inside part. So when I was doing the derivative of its outside, which was the middle, I kept 8 theta alone. I didn't mess with it yet. And then finally at the end, I'm going to multiply by the derivative of 8 theta, which is 8. So this part right here, that was the derivative of something squared. It was using a power rule. This middle part was the derivative of cosine of something. And then this last part was the derivative of, actually I should say theta, derivative of theta with respect to theta. This was the derivative of the very inside part, 8 theta. So you just basically keep multiplying by each derivative. They just all multiply together, and you keep the inside parts intact all the way throughout. So then I'll simplify this a little bit, and I get, for my final derivative, I'm going to multiply the 2 and the negative 1 and the 8 together to get negative 16 times cosine of 8 theta times sine of 8 theta. So there's my derivative of h using the triple chain. Okay, 3 derivatives multiplied together. And then just as a side note, you could also write this as negative 8 sine of 16 theta. So that was using one of our trig identities, and I want to see if you can look it up and figure out which one I just used there to simplify my answer a little bit. Now, would you be required to do that on a test? It depends. I've seen the AP test do stuff like this before, use trig identities to simplify their answer in a multiple choice question. So you would have to be able to take this answer and see how it's the same as that. But if it's a free response question, open-ended, then it's more than sufficient to stop here. But I want you to look up your identities and see what the heck I did here, and then tell me in class. We'll go over that in class. Why don't you try a couple triple chains? See if you can identify outside, middle, inside, and find the derivatives accordingly. Okay, so in part A here, hopefully you guys recognize that the outside part was this constant and power rule. 5 times the blop squared was like the outside function. And then the middle function again was cosine. So hopefully you guys caught that, cosine of this blop. And then the very, very, very inside part was, of course, the pi t that was plugged in here to cosine. So when you're doing your order of derivatives, we start with the outside one. So we did the power rule. So we do 2 times 5 is 10. Subtract 1 from the power to get 1. And we keep all of this inside part intact. We don't do anything with it yet. So it's just derivative of the outside with the inside parts plugged in. But then we have to multiply by the derivative of cosine, which was my middle function, which is negative sine. So that part comes next. And the pi t that was inside cosine stays inside of sine. We don't mess with it. And then at the very end, we finally multiply by that derivative of pi t, which was pi. So that was the derivative of the most inside part. So derivative of the outer part, 10 times the blob to the first, times derivative of the inside part, which was negative sine of the inside pi t, and then times derivative of pi. And then you see we have constants 10 times negative 1 times pi. So we can put that all together in the front. The constant is negative 10 pi, and then times cosine of pi t times sine of pi t. And we can leave our answer like that for part A. For part B, hopefully you recognize that the most outside function is e to a power. So all of this sign is all inside the exponent area for e. So that's like the inside. But there's sort of a middle and then a very inside part. So the middle part is the sine of blob. Sine of this part that's the most inside. So the thing that was like the most inside was x cubed minus 2. So that function got plugged inside of sine, and then all of that got plugged inside of e to the x. So it's a triple chain. So when you're doing the derivative, you start first with the derivative of e to a power, which is just e to the power. And notice how I kept the whole power intact. I didn't do anything with that at all for the first derivative. I just took the derivative of e to a power. So we did learn when you're taking the derivative of e to a power and you're having to use the chain rule, you just keep e to that same power, and then you'll multiply by the derivative of that power, which is what all of this is in parts, because we needed to do another chain rule. So then I had to multiply by the derivative of sine, because that was the inside part, so that was cosine. But I kept the x cubed minus 2 intact. I just left that inside of cosine. And then finally at the end, I multiplied by the derivative of x cubed minus 2, which was 3x squared. But it kind of looks weird to have the polynomial part at the end, so I just sort of moved it to the front. Of course, it doesn't really matter. You're basically multiplying these three functions together, exponential times a trig times a quadratic. But I don't know, usually we put the polynomials in front, so I just moved it. Lastly, we're going to end with an example where by simplifying with properties of logs first, we end up making this a much easier derivative to find. Because right now it looks like I would have to do a chain rule and a product rule and a quotient rule, which would be really challenging. So let's review some of the properties of logs really quick. So properties of logs say if you have two things dividing inside of a log, I'm just going to use natural log because sometimes students forget natural log is just a log base e. Then what you can do is take the natural log of each part separately and subtract. So that's called the quotient property of logs. So then over here, that means that I can say, okay, well, h of x is actually just the natural log of this part in the numerator, x times x squared plus 1 squared, and then minus the natural log of this part in the denominator. So still chain rules are having to apply, but at least it's not going to require a quotient rule. But there's another property of logs that says if you, inside a natural log or any log, if you're multiplying two things together, you can take the natural log of each thing separately and then add them together. So that could help me simplify this first part a little bit. So this function is really ln of x plus ln of x squared plus 1 squared, and then minus ln of the square root of 2x cubed minus 1. And then there's another property of logs that says, okay, if you have inside your log, you have something raised to some other power. You can actually take that power and bring it down in front and actually multiply it to the outside of the log. So I'm going to do that with this power of 2 here and with this power of 1/2. So then h of x is equal to the natural log of x plus 2 times the natural log of x squared plus 1 minus 1/2 times the natural log of 2x cubed minus 1. Now look at this. I can use the sum and difference rules, which as we know are way easier than product and quotient rules, and the constant multiple rule instead of chain rules. Although I will still need chain rules because I have this function plugged inside a natural log and then this function plugged inside a natural log. So these are like my inside functions. So for each of these derivatives, like these parts, this part, and this part, I will need to use the chain rule and multiply by the derivatives of their inside parts. So we just need to figure out what each of those derivatives would be. Okay, so here I go. And then I'm also going to use the derivative rule that says that the derivative of a natural log is 1 over the thing inside the natural log. And if you're using the chain rule with the natural log, we think of that as like ln of u, then it's 1 over u, right? U is this whole thing times derivative of u, which is what these guys are right here. Okay, so that's what we're going to use for this second and third one. So h prime of x is going to be 1 over x based on this derivative plus 2, because of the constant multiple rule, times 1 over the blob, 1 over u, so to speak, based on this rule right here, 1 over the whole thing that was inside there, times the derivative of the thing inside, minus constant multiple rule times derivative of natural log, which is 1 over everything inside there, times the derivative of the thing inside. Now I'll simplify a little bit. So I can multiply this 2 and that 2x in the numerator. So that's 4x all over x squared plus 1. Here I can multiply the 1 and the 1 and the 6x squared. And then 2 times 2x cubed minus 1, which would be 4x cubed minus 2. Oh, you know what? I could have reduced a little bit there. I could have done it right here because the 2 and the 6 can reduce. So let's reduce that here as well. Because if there's common factors, we should reduce them. So then that would be actually 3x squared over 2x cubed minus 1. And then we can just leave it like that. So we can leave it as 3 separate fractions. And that would be our derivative for this function, which, trust me, that process was so much simpler than using a chain rule combined with the product combined with the quotient rule. So always remember and use those properties of logs to your advantage. So that concludes our video. Thanks for watching.